Hello, everyone. So today I'm going to just make a short video kind of explaining the process of parametric vector form because it's honestly a really useful skill to be able to do, especially later in the semester in linear algebra. All right, so first we need to talk about what parametric vector form actually is. So you see it's made up of parametric, vector, and form, okay? So that vector part, this part right here, tells me that we're going to be working with vectors, believe it or not. The important thing here, though, is that we're talking about parameters. The word parametric tells us that we're going to be working with parameters, which are basically values that can change, that kind of affect our solution. So the basic principle behind parametric vector form is representing a solution set in terms of the free variables, because the free variables are going to be the things that are changing in reference to our basic variables, right? So let's try it. Let's see what happens, okay? So we're being asked to put the solutions to the homogeneous equation ax equals 0 in parametric vector form. So, first thing I see, ax equals 0, we have a matrix times some vector x is equal to the 0 vector. So I'm actually just going to write it out as a matrix vector multiplication equation, okay? I have this copied here so I can do this more efficiently. But if I were to do ax equals 0, that's the same thing as substituting this in for a, because this is a, times some vector x is equal to the 0 vector, okay? Now, it's important to be able to recognize what size our vector x is going to be. So since it's a vector, we can automatically assume that it's only going to be one column. So it's going to be some, I'll call it n times 1, okay? That's the size of this matrix or vector. So the important thing is, okay, how do we find the n, right? So we can see that matrix A has 3 rows and 5 columns. So matrix A is 3 by 5, right? Okay, and if you can't recall, when we're performing matrix vector multiplication or matrix multiplication, the two, depending on the order, the columns of the first matrix have to be the same number as the rows of the second matrix, okay? Otherwise, we aren't able to define matrix vector multiplication. So the way I tend to think of it is if I erase this right here, take away the 3's and the 5's. This is 3 by 5. This is going to be times some number here times 1, right? Okay, so I like to match up my middle pairs. They have to be the same in order for matrix vector multiplication to be well defined. We have no way of multiplying if we do not define it properly. So we know from deduction here that our number of rows in the vector x has to be 5. And whenever you're trying to find the size of the new vector that's going to be created, you just I just kind of cross out the middle. We've already used those to check. And whatever you have left on the outside, 3 by 1, is the size of your new vector. So I'm just going to write out the vector x up here. So this is the vector x. We know it's going to be 5 rows, so 5 tall. And I'm just going to say it consists of x1, x2, x3, x4, and x5. Those are our 5 variables that when we put in, when we put in here, we're going to be checking to see what values solve the homogeneous equation here. Okay, so if you remember correctly, how we usually go about doing this is using an augmented matrix. So we have something equals something, right? So our augmented matrix is going to be A, the matrix A with the 0 vector. That's our augmented matrix. I'll write augmented here. Augmented. Okay. So hopefully that makes sense. But our augmented matrix is really just slapping the 0 vector on the end, right? So I'm going to write out our matrix. 1, 2, 2, 2, 6, 1, 3, 8, 3, 1, negative 2, 2, 10, 0, 20. Okay, I'm going to put a little line here to designate that this is augmented. And the last column is supposed to represent our, like, the other side of the equal sign. And I'm also going to just, for my reference, going to label which columns are which. So this is the x1 column, x2, x3, x4, x5. So this is our lovely matrix. What do you think we do? Usually when we're solving anything in linear algebra, we tend to use our favorite tool ever. It's the RREF, or reduced row echelon form. And I actually have this down here. This is the RREF of our matrix. I'm going to bring it up just slightly. But this is what it's going to come out in the calculator as. All right. So I'm going to once again label x1, x2, x3, x4, x5. And then I'm going to call this like my equals sign column. And then this one is also x1, x2, x3, x4, x5, and our equals column. Okay, great. What does this mean? Why does it matter? That's a great question. Because why does it matter? Well, a lot of the time when we're working with matrices, especially in this course, we are representing a system of equations, right? So since this is representing a system of equations that makes this statement true, let's turn it back into one. Let's get it out of matrix land and get it into algebra land, right? So I'm going to draw an arrow over here. System of equations. Personally, I like working with some x's instead of just random numbers in a box sometimes. But what this means is that we have our x1 column, means 1x1 plus 0x2 plus 1x3 plus 0x4 plus 5x5 equals 0. That's what our first row means. I'm actually going to simplify this a little bit more to x1 plus x3 plus 5x5 equals 0. We don't need to take into account the ones and the zeros that we have there. The zeros multiplying the x2 will make it so it doesn't really affect our equation. So this is row 1. I'm going to label it row 1. Okay. For row 2, I'm going to go down here and we're going to have, I'm going to skip along and just not include my zeros because as you can see in the last one, they just disappear. But we can go along and we have 1x2 plus 1x3 is equal to 0. Okay. Remember that this last 0 is coming from this equal sign column on the right. And for row 3, we have x4 plus 5x5 equals 0. Great. Oh, sorry, you can't see that entirely. Great. Okay. What on earth does that mean? That's also a really good question. And what we need to look at now is our pivot columns. So whenever we have an REF, it's not a bad idea to look at the pivot columns just to see what's going on. So I'm going to change the color here to make this maybe a little bit more. Is not, okay. I'll make it blue and see how that goes. I'm going to circle all of our pivots. So we have a pivot here, no pivot in the third column, we have a pivot in the fourth column, and no pivot in the fifth column. And obviously we have no pivot in the last column, which is a good thing because that would mean that our system is inconsistent, which means that there are no solutions, which would be pretty concerning because typically, always, the trivial solution or the zero vector is always a solution. So we should not have that issue here. We must have messed something up if, when solving for the homogeneous equation, we got an inconsistent system. Oh, what happened? Okay. So, great. Okay, our pivot columns. What do they tell us? Well, that means that, ooh, what's going on? Okay. Sorry about that. I'm having some difficulties with my sheet. Okay. I'm going to move our system of equations just slightly over so I have a little more room to work with. But let's continue. Okay. So this has a pivot, this has a pivot, and this has a pivot, which means that those are basic. They're boring, they're basic, we don't like them. Okay, well, at least not right now. I'm going to use pink to label our non-pivot columns, or those also refer to our free variables, okay? They are free variables because they change in correspondence to our pivots, right? So let's think about this. I talked earlier about how parametric vector form is typically used to express our solution in terms of our free variables, because otherwise we would have a lot of messy work when it comes to trying to separate out our parameters. So parametric vector form makes it easier to work with these. So we're trying to directly relate our basic and our free variables together, okay? So with that said, let's continue. So we want to, in a sense, solve for our pivot columns or our basic variables. So if I go to row 1 and I decide, okay, let's, here, I'll write it out over here. 5x5 equals 0. Okay, how would I solve for our basic variable here? As you can see, the only basic variable that we can find here is x1. It's one of our pivots, and the other two are free variables. So let's solve for it. How would we typically do this algebraically? Well, I would subtract x3 and x5 over to the other side. So when we do that, we're left with x1 is equal to negative x3 minus 5x5, okay? So let's try it with the other ones, okay? x2 plus x3 equals 0. Okay, well, x2 is our basic variable, x3 is our free variable, so let's solve for x2. Okay, subtract x3 to the other side. x2 is equal to negative x3. Okay, and I'm just going to move down just a little bit. And for our third row, we have x4 plus 5x5 is equal to 0. Okay. So we don't have a basic variable here. Never mind. Why did I say that? I am so sorry. We do have a basic variable here. X4 is our basic variable here. Looking at the pivot columns, we can see that the fourth column, as I could not see apparently, the fourth column, X4 column, is a pivot column. So we do have a pivot in our last column, or in our fourth column. So solve for X4, which in turn we would just subtract 5x5 to the other side and get x4 is equal to negative 5x5. Okay, great. What on earth does that tell us? That is also a wonderful question, and I'm so glad you are asking all these lovely questions. And you know what I'm going to do? I'm actually going to copy and bring these down so I don't have to rewrite them. Because I, as a mathematician, am kind of lazy. If I don't have to do something, I don't want to do it. Okay. So I'm going to scroll up to the top briefly. And I want to remember that our x vector looks like this. That's going to be our solution. All right. So let's bring this down here and work with what we have. Okay. So we're trying to express everything in terms of our free variables. So that means we're going to try to get rid of all of our basic variables. So let's see what we can do with that. Well, we know what x1 is equal to. Okay. We know what x2 is equal to. We know what x4 is equal to. And I'm actually going to move this down just a little bit. And hopefully you don't disagree with me, but I think x3 is equal to x3. And I also think that x5 is equal to x5. You might ask me why that is something that I'm doing. Seems a little strange, right? Like, why on earth would I just be setting a number equal to itself? It'll kind of come through later, but it's important to be able to recognize, yes, that's true. The statement is true that x3 is equal to x3 and x5 is equal to x5, right? So let's substitute in, okay? So we have vector x is equal to x1, x2, x3, x4, x5. So let's try substituting in x1. Well, as we can see right here, x1 is negative x3 minus 5x5. Okay. x2 is equal to negative x3. x3 is equal to x3. I did not give myself enough space here. Let me move down just a little bit. All right. Oh, it cut off at the top. I apologize. Okay. X3 is equal to x3. x4 is equal to negative 5x5. And x5 is equal to x5. All right. Great. Now you might ask me, oh, can we just stop now? We expressed our free variables, our basic variables in terms of our free variables. Well, it's a little messy looking. I don't like to look at it like that. So it's not really helpful in this form. So let's see if we can split things apart, okay? So let's say I wanted to turn this into, well, let me rewrite this briefly. I'll write negative x3 minus 5x5. Okay, negative x3. And then I'm going to add a 0x5 here. It's not changing anything. 0 times x5 is 0, right? So, and the next one is going to be x3 plus 0x5. I'm going to say 0x3 minus 5x5. And then I'm going to say 0x3 plus x5. You might ask why I did that. I'm doing it to show that when and I'm actually going to move this down a little bit so I can have a little more space to work with in a moment. I'm trying to show that we have two, like, you can see there's on the left side of the equation, or the left side of the expression, sorry, it's all x3s. On the right side, we have all x5s. It looks a lot nicer just visually to see, okay, we have x3s here, x5s here. Well, we know how vectors work. We can add them together, we can subtract them, and we can scale them, right? So let's try separating these into two different vectors. I'm going to get one for my x3-like terms. So I'm going to take negative x3, negative x3, x3, 0, and 0. Okay. I got these terms from this part of this vector, right? So if I'm trying to get my x5s, I'm just going to take whatever's left. So I'm adding these two vectors together. So what just happened? Okay. I'm adding these two vectors together. So we're going to have negative 5x5 here. We're going to have 0 here, right? Because there are 0 x5s. I guess I should write out x3 after the x5. Or after the 0, I should write out what the 0 is multiplying. We're going to see that there is 0x5 in the third column, or the third row, sorry. There are negative 5x5s in the fourth row, and there are 1x5s in the last row, right? Okay, we are so close, right? So I mentioned two things we can do with vectors is we can add them and scale them, right? So we can also descale them in a sense. So what I'm going to do is I'm going to factor out or descale both of these vectors. So I'm going to copy this. I'm going to copy these two vectors, and I'm going to bring it down here just to get a little more space once again. Vectors take up a lot of space. And I'm going to factor an x3 out of the first vector, and that is going to leave me with a negative 1, 1, 0, and 0. Okay. Plus, oh, I forgot. I'm going to factor out an x5 from the second vector, and I'm going to be left with negative 5, 0, 0, negative 5, and 1. All right? Beautiful. Look at this. I can choose any value of x3 and x5, and I just scale it out, and that's my solution. I can solve the homogeneous equation with these, right? So just to put it in its last step, we're going to just say the vector x is equal to, move that over. Our vector x is equal to x3 times negative 1, 1, 0, 0. I'm not changing anything about our numbers here. I am just rewriting it to clearly articulate that our vector x that solves the equation is equal to x3 times this vector plus x5 times this vector, negative 5, 0, 0, negative 5, and 1. And this right here is our solution expressed in parametric vector form. It is in terms of our free variables. If you can remember from up here, our free variables are the x3s and the x5s. So this is our solution in parametric vector form. Now, I know that took a long time, and I'm so sorry, because I love to ramble. But if you do have any questions, let me know. Overall, I went through a really extensive, and it honestly, for many of you, it might be boring, explanation of parametric vector form, but it is a really important tool to be able to use in linear algebra, especially when we start talking about null spaces, other spaces. It is really useful to be able to represent our solution set in terms of these two vectors. So yeah, that's parametric vector form. You're a master now. You're gonna ace the class, and I believe in you. So have a lovely afternoon. Adios. And if you need any help with anything else, let me know. I'm here for you. All right, thank you. Bye.